inviting me. This meeting is being recorded. Let me share my screen. I hope also that is all working. So yeah, today I will talk about essentially two things. One is a little bit about the Event Horizon Telescope. I think most of you are probably familiar with it. So it's this global array of millimeter observatories around the world that together with as a very long baseline interferometry array is capable of reaching the required resolution to image black holes. So I'll start briefly with the latest results that we've obtained, so you can see what we're currently capable of doing with the EHT, and then I will talk about our next steps or updates in terms of the hardware, new sites, and so on that will prove the EHT in the near future, and what we hope to achieve then science-wise as well. And specifically, I will talk about the Africa Millimetre Telescope. So this will be the first millimeter wave dish in Africa. We plan to build it in Namibia. And as you can see here for this interferometry array, the AMT will hopefully, will provide very important baselines to, extend the EHT. So the first result I want to talk about from recent results from the EHT is what we obtained actually in April this year, or we published in April this year, which is polarization imaging of
Hello?
Excuse me. I don't know what happened, but we couldn't hear Dr. Janssen. So the other people, can you see and hear me?
We can see and hear you.
Okay. I don't know what happened.
Oh, hi. Sorry. Can you hear me?
Yes, now we can. Yeah, I don't know.
Problem. Yeah, it was on my end. I have some
suddenly it was just frozen.
Yeah, sorry. So I'm joining over mobile connection with my phone. I hope that will work.
Wow.
So let me share my screen again and try to continue. Sorry about this. And just to make sure, I hope that is okay. I will turn off my video because maybe that will also take some bandwidth away. So if I turn that off. Okay.
Thank you.
I think I managed to get through the first slide, right?
Yes.
Okay. Picking up here, right? So yeah, just a brief overview of the current results, what we can do with the EHT, just so that you get an idea of what we what we've been up to lately. So one of the latest publications was from April this year. This is our galactic center. In polarized light. So I guess you're familiar with these images, right? So these are the typical black hole images that we get with the EHT. We have, this dark spot in the center. This is the shadow cast by, the presence that there's an event horizon there. So it would likely be a black hole. And then you have this lensed ring of emission around it. So these are typically the black hole images that we get. And what's new here is that in this lensed image, we add these wind type of plots. So these indicate the electric vector position angle of the linear polarization of the synchrotron emission that we see here. So synchrotron emission, this is produced by the accretion flow and the jet, and we've now imaged this in linear polarization. So because it's synchrotron emission, that tells us actually a lot about the magnetic field strength. And because the linear polarization here, it actually goes up to fractions of about 40%, that actually tells us that they're very strong and ordered, highly ordered magnetic fields here present. We also tried to image Sagittarius star in circular polarization. So there is actually relatively strong circular polarization signal, but it's very difficult to constrain. So we tried our different methods, but as you can see here, they couldn't really agree on the structure because it's quite difficult due to the variability of the source and also the calibration in circular polarization to really narrow down the structure. So the only thing we could say about circular polarization is that there's upper limit of 6%. There's probably something there. It's probably also not so weak actually, but it's difficult to pin down. And if we then take these constraints, so circular linear polarization variability and a few other constraints into account, we can compare that against our theoretical models that we use to explain these observations. So these are general relativistic magnetohydrodynamic simulations, a very sophisticated simulation that we use to simulate these black hole systems. And if we take all the constraints into account and we look at our library of these simulations, there's actually only one that survives all of the constraints, and that's a MAD model with a very high spin actually. So MAD means it's a magnetically arrested disk. So actually that means that you have very strong, dynamically important magnetic fields. So that actually also accumulate a lot of magnetic flux near the horizon, which then erupt in very powerful outflows as well. So that fits actually quite well with the fact that observationally we find these high linear polarization fractions. There is, although actually two caveats here that I want to mention. One is that this is very model dependent, right? So it's only valid within the space of our GMHD simulations and the ones that we've looked at. So it's a very model dependent result that we have here. And the other thing is that we know that there is a rotation measure component here when we look towards the galactic center, when we observe Sagittarius star, which probably has an external component that is relatively static. So, in front of us and the black hole, and something that's happening, on horizon scales itself. So Faraday rotation happening on these scales in the immediate vicinity of the black hole. And our simulations are only able to capture what is happening, on this very small horizon scales here. So they can only, simulate the Faraday rotation on these scales and not anything that's happening in an external component. And we don't really know how much is coming, internally from the source and how much is from this external Faraday rotation. So the best, one actually assumption that we make here is that our conclusion that only this one model survives is only true if all of the rotation measure is coming from, external Faraday screen. If it's coming, for example, if everything's internal, none of the models actually survive. So we actually need also some work in improving our models most likely. So just want to mention that as a caveat that this conclusion is based, model dependent based on some assumptions, which are probably not all that correct, because in the end, the rotation measure probably is partially internal and partially external. Another result we've recently obtained was from last year. So this was also looking at our other source where we can image the black hole M87. So here we also looked at it in circular polarization. And again, a similar story. We have different methods and they don't really agree on the structure of the circular polarization here. Although here, I want to highlight one modeling technique in particular, which is this M-ring modeling, which is actually relatively robust for these type of observations. So you can see, across these are different days here. These two blocks and the rows are different frequency bands. And this method actually gives relatively consistent results, and it also performed quite well on our synthetic data tests. So officially, our statement is that also here we just have an upper limit on circular polarization. But if you ask, my personal opinion is actually that I do believe this, this dipolar structure and circular polarization that was uncovered by this M-ring modeling, because I think for this particular type of analysis, the M-ring modeling is actually better than the other methods that we're using. But if we then, just take again the Stokes V upper limit we derive from these observations, combine it with our earlier results that we've obtained for this source, also in linear polarization, we can again do, the same exercise, look at our theoretical model library, and see, which types of models survive all of the different constraints. And here there are a lot more models that survive than for Sergei star, but there's a clear trend that again you have these MAD type of models, which are these again strong magnetic fields, magnetically arrested disk, and the same models which have much weaker magnetic fields. And it seems that there's quite a strong preference in these observations for these MAD type of models. And then here it's scored for different spins. So probably the spin is somewhere in an intermediate range for this black hole and not at the very extreme spins. But again, a very model-dependent analysis. Then also this year, we've also, sorry, was there a question? I also hope I'm still not. Okay, I'm just going to continue. I'm hoping that my internet is also still working.
Yeah, everything is okay.
Okay, thanks. Right, so this is an analysis, where we've imaged the black hole M87 across years. So this observation 2017, 2018. The important part is that, the robust features that are predicted by GR and the fact that you have, a black hole there that doesn't change its mass, doesn't change its spin over these years, is that the size of this dark spot, this black hole shadow, and the size of the lensed emission ring around it stayed the same. So that was a very important confirmation for us. And what changed was essentially the position angle of this bright spot in total intensity here. So here, let's say something more along average position angle is maybe like this, and here it shifted to a different position angle within a year. But that's also completely understood from our types of models, because here we have a lot of emission, also from the turbulent accretion flow, which can change wherever you have a bright spot within a year. So that's perfectly expected. Then one example of another type of sources that we also observe, so not just M87 and Sergei star where you can image black holes, but other types of AGN where we don't have the resolution to reach horizon scales, but we can see the jet on larger scales, similar to other VLBI arrays that observe at lower frequencies. And this is an example of such a source. So 3C84, you can see here VLBI measurements at higher and higher frequencies. Now with the EHT, this was mostly a test observation. So if you look at the UV coverage, you see in black here, these are the EHT measurements. There are only very few measurements that we have of this source. We can't really even do imaging, but we can do a simple model fitting of the data. And when we do that, we find these three components here. One is the central core region, so the black hole probably somewhere in here. And then there's a western and an eastern component, which we interpret as essentially the launching points of a jet that has a very wide opening angle and is strongly edge brightened. So here, this would be the launching east and west. This would be where the jet is starting. And interestingly here, again, a very similar story, is that these components are also strongly polarized. So probably also in this jet, we have right at the launching region already quite highly ordered and strong magnetic fields. A little bit less, the core component is a little bit less polarized. So probably there on these scales here, they're probably a little bit more complex magnetic field structure that causes the resolution, a bit of depolarization, beam depolarization. So we have lower polarization fractions. So these are some examples, and here in the background of this slide, you can also see a few other examples, mostly of other AGN sources that we have observed. So you can see that I think with the EHT we're already doing quite interesting stuff, but everything we've done so far it was still limited in a few ways. So everything did was essentially monochromatic images, because we're a relatively small bandwidth. We're observing at around 230 gigahertz. So essentially all the images are monochromatic at that frequency. Also, all of the image reconstructions we did from single day observations, they're all static images. And with the observation of Sergei star, due to many uncertainties introduced by the variability of the source, limited UV coverage, and or still finite resolution, the best we could do as a test of GR, so we could say, our observations are consistent to within 10% with the current metric. So there's still a few things here that we want to improve. So now moving on to our ideas of how we can do some instrumental upgrades of the EHT. And really the focus in the near future is that we upgraded from an instrument that observes only at 230 gigahertz or 1 millimeter to a multi-frequency VLBI array. So many of our stations will be upgraded with multi-frequency receivers, and the goal is that we have tri-band simultaneous observations across the array, so observing simultaneously at 86 gigahertz, 230 gigahertz is what we're currently doing, and additionally even higher frequency of 345 gigahertz. Additionally, we have more and more stations joining the array. So since the images from the 2017 data, so our first images, we have the NOEMA array has joined, Kitt Peak Telescope has joined, the Greenland Telescope has joined. Also, in the latest observations, also KVN dishes are also joining when they're capable. So I think 2 by now that can do 230 gigahertz observations. And of course, what I'll talk about in a moment is you can see here that we also will have, if we build the Africa Millimetre Telescope, we significantly expand also our baseline coverage to the African continent. So it would be a huge improvement to where most of the other telescopes are lying. Additionally, this was one example of EHT as a multi-frequency VLBI upgrade, but there's a lot of synergy then with other VLBI arrays that are also doing similar things, trying to upgrade their current operating systems to also multi-frequency VLBI arrays. And many of these developments are driven actually by the KVN development, which by now they have been pioneering this work. And the latest what they can do is that they have actually 4 band simultaneous observations at 22, 43, 86, and 129 gigahertz. And as I said, some of them even can do 230 gigahertz. And related to that, there are many European dishes that are now being upgraded to following the same developments and also doing mostly actually 3 frequencies simultaneously, but we would then have also a big global multi-frequency VLBI array here, very complementary to the EHT. And of course, if we're thinking now about the AMT, our hope is of course that we have, it will be a millimeter VLBI, a millimeter dish. So we will have receivers that are able to allow us to join EHT observations, and also these observations that are still in the millimeter range, but a little bit longer wavelength. But additionally, we really want to also put centimeter wave receivers on the telescope, so that in the future we hope to be able to participate also in an African VLBI array that will operate mostly at centimeter wavelength. So if we look at what this could mean in the future, we could have EHT array that could transform into something like this. So our current observations, they look like this: single frequency, 230 gigahertz. You have a UV coverage like this. Now, if you think about a bit further future, where a lot of more telescopes might join the array, and we have these tri-band triple frequency band observation capabilities, you can have from very limited UV coverage, we could get a UV coverage like this. So we really are very proper interferometer here with a really good UV coverage, significantly improved dynamic range and imaging capabilities. And I want to mention that also we've recently published our first test observations where we actually have shown that we can do VLBI at 345 gigahertz. So you can see here are some detections that we were able to obtain in our first test at VLBI at 345 gigahertz. The problem here is that you're very much sensitivity limited. So there's this technique also being pioneered by the KVN, which is called frequency phase transfer, that you will need to really get, from these first test observations with a few detections to something like this, where the green points here are the projected detections, fringe detections at 345 gigahertz. Because with this frequency phase transfer techniques, if you're simultaneously observing at 86, I'll give you an example, 86 and 345 gigahertz, you can transfer the phases that you've obtained at the much more sensitive 86 gigahertz from the 86 gigahertz VLBI data to the 345 gigahertz data. So you're essentially extending significantly the coherence time of the 345 gigahertz data, which is very short, actually intrinsically due to precipitable water vapor in the Earth's atmosphere. But with frequency phase transfer, you're able to overcome that and are able to get the required sensitivity also at these highest observing frequencies to really have enough UV coverage to do imaging. And the type of science that we want to do here is this is one summary slide that shows you some ideas, actually what I find most interesting of what we can do with such a multi-frequency VLBI array. The first thing is that we can see this interplay between the accretion disk and the jet. So the disk-jet coupling essentially live in action and resolve actually what is happening in the jet and what's happening in the accretion disk. The key technology here is that we have the lower frequency observations that have enough sensitivity that we can actually detect the jet. And then with the multi-frequency, specifically 230 gigahertz and simultaneously 345 gigahertz, can look at the horizon scale emission, and then we can compute things like the spectral index and the actual rotation measure, which, if you recall, was also major uncertainty in our current observations. And with these observables, we're actually also able to distinguish on horizon scales what type of emission is coming from the accretion flow and what is coming from the jet. So in our two sources, M87 and SAAO, we can really trace essentially live on different time scales. So for M87, it's months. For SAAO, because the black hole is so much smaller dynamical time scale, that the time scales will be on hours. We can trace what is happening with the accretion flow and then simultaneously what is happening with potential outflows. Certainly in M87 and in SAAO, we can maybe try to understand if there's a jet at all. Then for GR tests, the main thing is, for SAAO, we really need the 345 gigahertz data because we have higher resolution, we get sharper images. We can look at achromatic features produced by GR in our images, and at 345, we also are less affected by scattering. So we really think that with these type of observations, we're able to significantly improve our current constraints on GR, and if the observations are in agreement with the current metric. And for this, you also need this, as I mentioned before, lower frequencies, so 86 gigahertz for frequency phase transfer. Then highlighting one study in particular here that was done by Noemi Labella, a PhD student at Radboud University, who has shown that the AMT, if we're able to add it, if we will add it to the EHT, due to the nature of these baselines that we're getting, has actually the highest impact for dynamic reconstructions of SAAO. So far, we know that the source is variable. It changes over the course of one observing run of, let's say, 8 to 12 hours a day. But our baseline coverage and sensitivity is not really good enough that we're able to reconstruct the movies. Instead, we reconstruct a static image while the underlying source is actually changing a little bit. But Noemi has shown that with simulations, if you add the AMT to this array, it will significantly improve our capabilities to actually do a dynamic reconstruction of SAAO. So certainly, when the AMT comes online, we'll get very high fidelity, ideally also multi-frequency movies of the accretion flow and the emission of SAAO on horizon scales. So with that, I think I only have a few minutes left, so I'll try to speed up. Want to tell you a bit about the key specification or what our plans are for the Africa Millimetre dish. So it will be a 15 meter class dish. We're targeting an optimistic first slide by 2028, and we're in the final process of selecting the site. So we have 2 candidate sites in Namibia, One that has already the infrastructure present, so this is the HES site, so this is our backup site. In case our preferred site, which is a higher site, so it's better, more stable atmosphere, which is on top of the Gamsberg mountain. Here I want to highlight specifically also the work done by PhD student Lord Franz at University of Namibia. Who spent a lot of work characterizing the atmospheres at those different sites using a lot of instrumentations, models, and also the most recent data that we now have from radiometers that are installed on these sites. And our receivers, we have one very broadband multi-frequency receivers that will cover multi-frequency EHT array, but also the what I showed you, KVN plus European, so KVN plus EVN array, and also centimeter band receivers, so that we can co-observe also with Africa VLBI network and the SKA. Currently, what we need to resolve to be able to make the Gamsberg site accessible is the road. So the current road is in very bad condition, so we either need to build a new road or refurbish this road. The idea is then with that, once we've fixed the problem of the road, we open up the Gamsberg mountain as actually a general astronomical observatory site, because the optical seeing, for example, on Gamsberg is comparable to La Silla. So once we make the site accessible, the AMT might be just the first telescope there, and then many other telescopes, specifically for optical telescopes, will be an excellent site that could then follow later. Okay, very brief here. These are, you can also ask me about this later, site differences between the two locations. The main thing is that the highest frequency, 345 gigahertz, is probably only possible on top of the Gamsberg mountain. Also on Gamsberg, you have many more days where you can actually do 230 gigahertz VLBI. And for single dish, you can see that there's the main thing will be 3 millimeter signs. There you will have a 10% increase in sensitivity. Actually, at 1 millimeter, the Gamsberg is 60% more sensitive due to the better atmosphere. And you can translate that here, for example, this was done for one AGN survey, so one of our science cases, where you can see that if we look at this lower row, that to do the same type of science at the HES location would need 17 days of observing time, whereas in Gamsberg you could only do it in 6 days. So it would be much more efficient and more science to be done. And I want to highlight one thing, because it was based actually on a software that was developed in South Africa by a group around Roger Dean, which is this Max Silhouette software that we've coupled to one of our calibration pipelines to do this full end-to-end modeling of the VLBI signal chain. So you put in a theoretical model, you get out your simulated observations. So I want to highlight this because we're actually using exactly this software to do these predictions of what the AMT will be able to do in terms of VLBI and the impact it will have for the EHT. And related to that, there's also, I think, a very exciting work, also led by, this is from the group of Roger Dean, and it's a student, Sankosi, who is now looking, I found this work very exciting, who's now looking at candidate sites also in South Africa, where you could also build a millimeter wave dish to also join the EHT. And the nice thing is there's, for example, I'll give you one example, there's a Sutherland site. You can see comparisons here. So Sutherland is in orange, and you can compare it to the the dashed line, which is the Kitt Peak site, which is a site that is already in the EHT, so it's operating. And you can see that there are many months, for example, May, which is close to the typical EHT observing window, where Sutherland would be comparable in quality to Kitt Peak. So Sutherland really is a viable site to join the EHT, particularly if the AMT has already been built, because with the AMT already present, any site in South Africa will have a relatively short baseline, so short compared to the global EHT VLBI array. And with this short baseline, you have one very sensitive baseline that will help you to get your fringe detection. So with the AMT build, it will be much easier to build additional telescopes in neighboring countries like South Africa to also join the EHT array. Yeah, I don't know how much, do I have still some minutes to talk maybe a bit about the single dish science of the AMT, or?
Yes, no problem. You can continue.
Okay, okay. Just tell me when to stop then. So these are just a few science cases for what else we want to do with the ANT besides when we do VLBI, so joining other VLBI arrays. And I mean, most of the time we will do this type of single dish science because VLBI you can probably only do a few days in the year. So one science case is monitoring of AGN sources. So you have already gamma ray observation now with HESS, in the future with CTA of southern sky sources. So you can monitor it also then with AMT and millimeter wavelengths to understand the correlation between millimeter and gamma ray emission. You can have, let's play this movie. This is a light curve measured of Sagittarius star. So from Namibia, you can get very long integration times, very long light curves, also then multiple frequencies to look at things like time lags, to understand also the variability of Sagittarius star to get a better understanding of the nature of the accretion flow. And this is probably the biggest single dish science case. It will be the transient observation, so mostly transient follow-up. Here's one example of an X-ray binary in outburst. You can see that at the higher frequency observations, there's a lot of structure in the light curve. And here, if you model this, actually, this was done, I think when the author modeled this, they found that in the short time range, there were multiple discrete jet ejections happening in the source. There are a lot of millimeter stellar flares. It's not really my area of research, but I understand that also SPT, for example, found some flares also from M dwarfs, which was not expected because they are not known X-ray emitters, so they may not have hot X-ray corona. So it's unclear, at least to me, where those millimeter flares could come from these sources. And then there will be a dedicated program to do a rapid follow-up of gamma ray bursts. So after getting a trigger from a gamma ray burst from, say, X-ray satellite, trying to be very fast with this small, very quick telescope that can actually move fast, to be on source and try to get some immediate follow-up of the millimeter wave emission from this gamma ray burst. And the interesting thing is that according to some models, it is predicted that actually from the reverse shock emission, that there should be a lot, so the sources should be quite bright at millimeter wavelengths if you're able to be minutes on the source after an outburst. But in a recent survey from the Atacama Cosmology Telescope, they have not found a single, not found any millimeter emission from a gamma ray burst. So it seems to me maybe these models are a bit too over optimistic about the amount of millimeter emission that is coming from these gamma ray bursts, which is, in my view, another motivation that we need to add these lower frequency receivers as well. So certainly we have 35 gigahertz, maybe also something like 22 plus 8 gigahertz receiver would be great to see. If we don't detect it at millimeter wavelengths, will we then see something at shorter wavelength where we have much more sensitivity? And this will really be, try to be on source minutes after outburst. And to my knowledge, the quickest radio follow-up that was also done at centimeter wavelengths that was done so far was gamma ray radio emission from a gamma ray burst 32 minutes after the outburst. Then also something that I also found really exciting was a recent paper that has shown that several days, I forgot what it was, 17 days, top of my head, something like that, after the outburst of a gamma ray burst, I found that the millimeter light curve was re-brightening. So maybe that there was at some point a later reverse shock happening. So the other light curves, there was no increase, but suddenly there was this bump in millimeter light curve. So that also tells me that maybe if you don't detect the millimeter emission right away, or if you're a little bit late on source, it's still worth to monitor these sources for a longer period and see if maybe later on you catch some millimeter wave emission. Yes, very quickly, we also have a science case of astrochemistry. So where, because we have these broad observing wavelengths, it's worthwhile to do very deep integration of these dust clouds in the southern sky to look specifically a little bit at the lower frequencies at organic species. There are also interesting VLBI application with astrometry, actually, that you can do with millimeter VLBI. This is also enabled by this frequency phase transfer technique, where if you also do this, also include observational multiple sources, then you have the source frequency phase referencing. Then you can actually do very well, very precise astrometry at millimeter VLBI. And give you a few examples of what this could mean in practice. Would be, for example, that we have more observations of southern sources for the International Celestial Reference Frame, and particularly at some shorter wavelengths, so particularly at Q bands, so 7 millimeter, where which is yet unexplored, and where people are working on to extend these ICRF sources into more of the southern sky and at higher frequencies. So the AMT will be, I think, be able to make a big contribution here. One other point is that the black hole shadow itself is actually an excellent reference point if you compare it to other AGNs that are typically used at reference points at lower frequencies, because unlike those AGN sources, the black hole shadow doesn't have any moving component. It's really a static, source, and there's no complication due to a frequency-dependent core shift that would usually happen in the jets of those AGN. And of course, relatively well-known science case in the galactic center. You can use also a combination of millimeter VLBI and near-infrared observations, specifically of Gravity Plus after the upgrade, where you can do off-axis fringe tracking, where you can observe a common set of maser sources to align the millimeter and the infrared reference frames of our galaxy. I think I'll skip this in the interest of time. This is about some software development that we're doing to catch up with these expanding EHT arrays of more telescopes, more observations also per year, and more frequencies. Just mentioning this in case there are questions on this. Happy to discuss this later. And now, sorry for being 10 minutes late. I'll just have here my summary. So we are in the project very excited that AMT will come online soon as the first millimeter wave dish in Africa. For the EHT, the biggest impact will be on dynamic reconstruction of Site J star, but we will also join many other VLBI arrays, and we have a broad range of also single dish science cases. And if you're interested, please get in touch. I'm happy to discuss or to invite you to our monthly meetings where we discuss these science cases. And what I haven't really mentioned so far, but was also important to realize, is that in the southern hemisphere winter period, we have excellent weather together with ALMA telescope and APEX to do really 345 gigahertz VLBI together in the time from June to August, which is not really possible with many of the other EHT sites because they're in the northern hemisphere. So with that, I'd like to end. I hope my connection is still working. I'll try to stop sharing. Thank you.
Okay, thank you so much. Yeah, everything worked well. No worries. It was a great talk, and I think very exciting news for the Africa continent. So let's see whether anyone has any questions. You can either raise your hand or just unmute yourself and ask.
Maybe I could just ask, you mentioned the tests of GR if you have better imaging. Could you maybe say a little bit about, what you might look for, what, how much better does the imaging have to be to see something which would make us suspicious of GR?
Yes. Yeah. Okay. Yeah. I don't think we will be suspicious of GR. It's more, so what we will test is if there are any deviations from the Kerr metric, right, that would explain our observation. Of course, the expectations is that there are none, but that we would go, from 10% deviation to something smaller. The main thing here is, well, there are two several competing effects here, and to be honest, right now I can't tell you which one is the most important, so I'll just list them all. So one is the scattering, the interstellar scattering. So with that we have, there's more blurry emission ring if we go to higher frequencies, or even do these multi-frequency observations where we can solve for the scattering screen. We'll resolve that, and essentially this blobby thick ring of emission will become thinner. And with that we have a better constraint on the size of this dark spot in the center, right? This black hole shadow. And the size of this black hole shadow is directly related to the mass over distance of the source, and the possible presence of and the metric of the black hole. So because we know the mass over distance very well from measurements at the infrared, these stellar orbit measurements, if we then combine that with a better constraint on the size of the shadow, we get in turn a better constraint if the observations are still in agreement with GR. For example, if you know the mass and the distance, but the black hole shadow suddenly is a factor of two probably not, but let's say 20% larger, the current observation is difficult to see that. But if we have a sharper image, we'll be able to see this deviation, and that will be a very clear deviation from Kerr, because from the Kerr metric, even if you don't know the spin, the size of this dark spot is very well determined, very well predicted. So scattering was one effect. Then also higher frequency at 345 gigahertz, so naturally have a better resolution at the higher frequencies. That will also help, and the ability that we can make a dynamic reconstruction, because due to the fact that even though the source is varying, we're fitting a static model to the observations. By essentially what we're doing is we're inflating a little bit the error bars in the data to capture this possible variability. So that again introduces additional uncertainty, which makes the image again less certain and a bit more blurry, simply speaking. So if we have it's more baseline specifically with the AMT, and we can do an actual movie, we will again increase the sharpness. So these are the three effects, but we haven't really done an in-depth study to show which one is, if any of them, is more important than the others. It's a bit maybe just hand-wavy argument, but that's our current thinking about this.
Okay, thank you so much. Any other question? Okay, I don't see any question.
Yeah, I've got another question if you don't mind.
Sure. Oh, I think there's another person too.
Please go ahead, Catherine. I'll go after you.
Okay, thanks. I was just thinking, with the Meerkat observations of the center of the galaxy, there are all these filaments that have been observed. Do your observations of the center of the galaxy throw any light on what these filaments are observed at higher frequencies?
Okay. Yeah, good question. So our problem is, of course, that because of the very high resolution, we have a very small field of view. So in our standard field of view, those filaments are completely resolved out. So what we would need to do is, and I haven't done that calculation, but we should check if those filaments are expected to be bright and compact enough at our observing frequency. And my feeling is that probably they're too extended, and I don't know how bright they really are at millimeter wavelength. But let's say that they would be very bright, then we could also do actually on a correlation center, put them on some of these filaments and see if we can image those structures. But my feeling is that with EHT VLBI, our sensitivity is probably not good enough for that, and rather first try to image them, which maybe has been done already, I don't know, but with ALMA. I think the ALMA array would probably tell you much more than the EHT here.
Okay, I think Senkosi, you can go ahead.
Hi, Dr. Janssen. Thanks for a really cool talk. So I was excited to see that you now have radiometer data from Gamsberg, and I was wondering if you've performed a comparison, and if so, how those radiometer data compare with um, the results obtained from meteorological modeling, such as those that were presented in Alex Raymond's 2021 mass survey of potential NGEHD sites.
Okay. Yeah. Hi. Thanks. Didn't know that you're also here. Good to hear from you again, Senkosi. We have the radiometer now, and actually also see Michael Backes here on the call, so he knows many more of the details than I do, because it's him and his PhD student Lot who is working on this from the latest plots. And I think it's pretty much final now. So we're pretty convinced of what we're seeing is that we get a very good agreement of the radiometer data and the GNSS and the MERA2 data. So I don't have a plot with me right now, but if you write me an email, I can probably send you those plots. So you see that there's a very good agreement, essentially a linear line that you can fit to the two data sets. And the only thing that is then left is a small overall offset. So what we do with the radiometer, because we only have it from limited data, we compare it against the GNSS data that we have over 2 years to find out, the offset between those two measurements. And then we have, from the 2 years of the GNSS data, which are then validated against ground truth radiometer, we take those 2 years and compare it to the MERA2 data, which spans many years. And then we get another good agreement between MERA2 and the GNSS. We derive another offset. And then we have essentially the MERA2 data calibrated very well against GNSS and then the ground truth radiometer. And then we have from the MERA2 statistics over many years, and we then use that data to make a prediction with good statistics for what is the most likely PWV value that we can expect for future observations. And then there was, second part of the question was something about NGEHT. Maybe you can repeat that.
Oh no, I think you've basically answered the question. I was just asking how the radiometer data compare with the results presented by the study by Alex Raymond about it was a mass survey of all of the climatological conditions above the NGEHT sites that are being considered. But I think you've answered the question.
Yeah, maybe to 80%, maybe, because I think that Alex used the MERA2 data, but I am
Yes, he did.
not. Oh, okay. Yeah. So in that case, I think maybe Michael Backes, if he's still here, I thought I saw him. You can say roughly what the overall, there's a small offset, maybe 1 or 2 millimeter. So the MERA2 is pretty good. But if you really are in the regime where you want to know exactly what it would be, then there will be a small offset. But again, I'm not sure, Michael, if you want to add something, if you're still here.
I'm here by fighting a bit of microphone. I can't exactly remember the numbers there with us and that. But so the two major
Sorry, can you just talk a bit louder, because we can't hear you well.
Okay. Give me a second.
Oh, yeah, maybe different microphone needs to be selected.
Okay, is it better now?
Yes, thank you.
Okay, just switch microphones. So the one take-home message is certainly that, of quite a bit to my personal surprise, we found essentially perfect a match between the GNSS estimates of the PWV and the radiometer estimates. So those are really in perfect agreement with one another. And they're still in good agreement with the mirror data, but there is quite some offset. So, but that's sort of what you would expect. The satellite measurements never give you ground truth. That's why you always, well, at least to my experience, always have to rely on ground measurements.
All right. Thank you. Sounds very positive.
Okay, thank you so much. If there is no more questions, I think we can end the meeting now. Thank you again, Michel.
I had a question.
Okay, sure, go ahead.
Yeah. Have you given any consider? You talked about co-hosting other instruments. The SKA Africa configuration includes sites very close to the AMT site. Is there a possibility of co-hosting an SKA antenna at the AMT site that would allow for shared resources, etc.?
Yeah, I think so. I'm not. Maybe I would need to talk to more of our project managers to see if there are any constraints. But naively, I would think that that's a very good idea. At least, let's say, from the perspective of the AMT, because we would benefit from this, of course. For the SKA dishes themselves, for example, if you think about the difference between the Hess and the Gamsberg site, there's probably not that much to be gained at those lower frequencies. So if there would be interest from the SKA sites to work together here and share resources, then I think that we would be very welcome, very happy to collaborate.
Yes, there is already an SKA antenna planned for Botswana. So that would immediately give SKA baselines. And the AMT is going to be under pressure for millimeter observations. So that SKA dish would relieve any demand at centimeter wavelengths.
Yeah, or you go. Yeah. Oh, sorry. Go ahead.
No.
Yeah. I would even think that you could, depending on the difference between the two, you could run it also as a small mini interferometer, depending on data access, where when the AMT is not doing millimeter science, you could have both dishes observing also at centimeter at the same time.
Thank you. I don't know whether, George, do you have more comments? Okay. Okay, anyway, I think we are almost out of time. So I'm sure if anyone has any more questions, they can probably email Michel. Am I right?
Yes, of course.
Okay. Thanks again for the great talk. And thank you everyone for attending. And we'll see you hopefully in the next SAAO Colloquium. Thank you.
Thank you very much. Goodbye.